Hi there guys, my name is Miss Chelsea and today I'm going to talk about Module 4 with you guys. It's going to go over Chapter 11, Transformations, Symmetries, and Tilings. And let me get it pulled up here. Alrighty, so on the very first question, which is pulling up here on my screen, it says that Ephraim and Devontae were given the pattern blocks that are shown on the left and to reflect it over a horizontal line within the center of the square. So here is the first set of blocks that they were given, and then they were asked to reflect that over a horizontal line. So this is what they got. We are asked what type of rotation was used for this. So we all know that a complete circle is 360 degrees, and half of that is 180 degrees. And the reason I say half is because if you notice, let me turn my little pointer on here for you. If you notice that these triangles here at the top, they are now on the bottom of the second figure. And then we have the square in the center, which is still in the center. And then the last shape is at the very top of the figure. So if we were to have a horizontal line straight across and they flipped it, they did a 180 because instead of it going all the way back around the circle, it only went halfway. So it would be 180 degree rotation. So the next one, number 2, we're given a group of shapes, and within those shapes we are asked to find a few different ones in particular. So the first one, we're looking for a shape that has one line of symmetry but no rotational symmetry. And what rotational symmetry is if it's flipped 180 degrees, then that shape will still be the same flipped as it was originally. So for this one, they're not supposed to have any rational symmetry, but they are supposed to have at least one line of symmetry. And what the line of symmetry is for example, here on the triangle, if we were to draw a line at one point in the within the shape, and we were to basically flip that shape over that line, it would make the same shape. So, for example, the triangle does have a line of symmetry. Now, some of them may have more than one line of symmetry. So for this one, we're just looking to make sure that it does have at least one. And then the next one we have here is a semicircle. The semicircle has one line of symmetry. I'm not sure why there it is. All right, the semicircle does have only one line of symmetry. If we were to flip the left side of that semicircle over the line of symmetry, it would be the exact same on the other side. Then we're given another equilateral triangle here, turned sideways, and it also has one line of symmetry, only the one. If we were to flip it down onto the other side of that line, it would be the same. Then we're given a rhombus, and it has one line of symmetry shown here, but it would actually have two. We could put one through the center horizontally, and if we were to flip it, it would be the same on that one as well. And then we have a rectangle. Again, the rectangle does have more than one line of symmetry, because if we were to draw that line horizontally as well, we could flip it again. And then we have, here we go, let me pull that up. We've got a hexagon here, and it has one line of symmetry shown here in the middle, but it could also have more than one as well. But it does have at least that one line of symmetry, so it qualifies for this first one. The next one is asking us to have the rational symmetry that we talked about, which is if it was flipped 180 degrees, that shape would still be the same as the original shape. But we don't want them to have any reflection. And what reflection is if, say, we had a mirror up against that shape, the reflection that you see in that mirror is going to be the exact same as the original shape. So these are going to be the ones that we do have rational symmetry, which again means if it was flipped 180 degrees, it would be the same. So first, we're going to look at 90 degrees. So if we were to turn this rectangle 90 degrees, it would stand up vertically. So it is not, 90 degrees does not qualify it as rational. And then this next shape, same thing. If we turn it 90 degrees, it's not the same. Same with the rhombus. in this last figure here shown. But if we were to turn them the full 180 degrees, all of these shapes are rational. They all have rational symmetry. Because if we were to flip that shape halfway around a circle, it would be the exact same. Same with this figure. A rhombus would also be the same. And the very last figure would also be the same, flipped 180 degrees. And then we're going to move on to number 3. And Myra thinks that this, oh, I'm so sorry, I skipped the very last one on here. I apologize about that. For the last one, we're doing one line of symmetry and rotational. It can only have one line of symmetry within it. It cannot have multiples. And it also has to be rotational, which again means if it's flipped 180 degrees and it's still the same, then it is rational. So for the first shape here, we have no line of symmetry because there's our line of symmetry there in the center. And if we were to flip that top portion over onto the bottom, it is not the same. So that one is not, it does not meet the criteria for this portion of the problem. Next, we're going to look at the rhombus. It has a line of symmetry through the center, going horizontal and vertical. So that automatically disqualifies it for this problem because it has more than the one line of symmetry. We're only looking for at least one line. So that one also does not qualify. Then we're going to look at this figure and we're going to put a line of symmetry in there. And if we were to flip the left portion of this figure over that line of symmetry, it would not be the same. So it does not have a line of symmetry, and that there automatically disqualifies it from this problem because it's not the same. If flipped over, there is no line of symmetry. Next, we're going to look at a semicircle. For the semicircle, we do have one line of symmetry here. And then if we were to turn it 180 degrees, it would not be the exact same. So it does not have rotational symmetry either. It does not count. Then we're going to look at a triangle. Here's our line of symmetry through the center of the triangle. And then if we were to flip it 180 degrees, does it look the same as it previously did? No. So that is going to disqualify it from this problem. Next, we're going to look at the rectangle. We've got one line of symmetry going horizontal. And then we also have one going vertically. So that automatically disqualifies it. We only need one line of symmetry. And then we're going to look at this equilateral triangle here over on its side. We're going to put a line of symmetry there. If we flip it, it does qualify. It only has one line of symmetry. But it has to meet the criteria of both the one line of symmetry and rotational symmetry. So if you see here where I flipped it 180 degrees, that is not the same shape that we started out with, so it does not qualify at all either. So for 2C, looking for one line of symmetry and rotational symmetry, we do not have any of the shapes that were given to us that meet that criteria. So there are no shapes given. Now we're going to move on to number 3. And for number 3, Myra thinks that this shape here, this given figure, is a vertex figure. And we are asked to find out if it is a vertex figure or not and why. So for it to be a vertex figure, what we want to do is have all of the angles within those add up to be 360 degrees. So what do we do to find out the angle degrees? We're going to use the formula n minus 2 times 180 minus n. Sorry about that typo there. I do have a 2 at the end that is supposed to be a letter N. The letter N is going to stand for the number of sides that are in each figure. So we're going to look first here at the pentagon, and we see that the pentagon has 1, 2, 3, 4, and 5 sides. So for the letter N, we're going to plug in the number 5. That gives us 108 degrees for the pentagon. Next, we're going to look at this hexagon here. We have 1, 2, 3, 4, 5, 6 sides. Excuse me. So we're going to plug in the number 6 for the number of sides, the letter N. That is going to give us 120 degrees. Next, we're going to look at the octagon here, and we're going to count the sides. 1, 2, 3, 4, 5, 6, 7, 8. Now, if you know the shape that you are given and you know automatically that it has a certain number of sides, just go for it. If you're not sure of how many sides it has, just count them like I did just now. I added some stars to make it a little easier. Some people know octa means 8, octagon, there's 8 sides. So if you know them, just go for it. If not, it's pretty simple, just count the sides. So we're going to plug 8 into our equation here, and we're going to get 135 degrees. Now, we need to add up all of those angles and see if we get 360 degrees. So if we add all of those up, 108 plus 120 plus 135, we get 363. For it to be a vertex figure, remember it has to equal 360. So this number goes over the 360 by 3. So what we're going to do now is we're going to look at that figure and see what we could do to make it a vertex figure. So here's our original figure we are given. And we just need to simply subtract 360 from 363, or you can just simply look at it and know that the difference is 3. So we're going to make a 3-degree gap, which would make our figure a vertex figure. Super easy. Next, we are given this figure here. And for the first portion of this problem, we are asked how the triangle QPT, if you look here, we have Q, P, and T, this triangle here, how it is congruent with the triangle SPT. So congruent just simply means that it's exactly the same when it is superimposed upon itself. So if it were flipped over this line of symmetry here in the center, it's going to have the same reflection. So I have it highlighted here for you. Triangle QPT is in yellow, and then the triangle SPT is in orange, and our line of symmetry is highlighted in purple. So if we were to flip the yellow side over that purple line of symmetry, it would match up evenly with the orange triangle. So that is how we know that it is congruent. For the second figure, we have the same exact figure. The question is a little bit differently. We're trying to find out how angle QPT is congruent to the angle SPT. So the angle is the interior here on these triangles. So we're going to look at angle Q here on the QPT. It lines up. If we were to flip it over that line of symmetry, it would be the exact same as the angle of S on the SPT. Then we're going to look at P, the angle P on both sides of these triangles here. If we were to flip it over that line of symmetry, we would be even with T, angle T down here. So that's how we know that the angles are congruent to one another. Again, we're given the same exact figure. The question just changes just a little bit here. So for the third figure, we're asked how is the triangle QPV congruent to triangle SPV? So we've got QPV. We're given this little triangle here. And then how is that congruent to SPV? If you follow my little laser here, we got S, P, and V. So to know that that is congruent, again, if you flip it over that line of symmetry, it is going to be the exact same. So I've got it highlighted here in yellow for you, the first triangle. And then you see here in the center, the one common point that they share is V. And then here's the full triangle. And then, sorry about that. You can see that it is congruent because if we were to flip over QPV, it would be the exact same as SPV. And then again, this is the last one, I promise. We're given the same figure again, but we're asked why angle QPV is a right angle. Now remember, a right angle means it is 90 degrees. So we're asked for QPV. Follow my little pointer here. We have Q all the way up to P down to V. So this triangle here, we're asked how it is a 90-degree angle. Well, if you remember back when we were looking at an angle, if it was basically an L shape, that little angle right there, that is 90 degrees. So if you look at this, it's 90 degrees. And then also on the other side, it is also going to be 90 degrees. All right, let's take a look at number 5. For number 5, we are asked to construct a regular pentagon labeled penta, P-E-N-T-A. And then we're asked to construct an equilateral triangle labeled PQR. So here are both of these figures. On the left here, we've got the pentagon, and I've labeled it P-E-N-T-A, penta. And we have our equilateral triangle QPR, or PQR, I'm sorry, I said that backwards. And then we're asked to inscribe them. So here's what that is going to look like once they are inscribed. We have this larger shape inside of a circle. So first, what we're going to do, we're going to try to find the degree of this particular angle, NO to Q, this triangle here. We're going to try to find out the angle there, the degree of that angle. So what we're going to do first is we're going to pull out that pentagon. First, you're going to see this little triangle I have here, though. If you notice, it is QOP right here, this little bitty triangle. And if you remember, a triangle is going to have all the angles inside of that triangle are going to equal 180 degrees. So for this one, we have two angles that are exactly the same, and then we have one that's a little bit larger. And normally, remember, if it's an L shape, it's going to be the 90 degrees. And this one is actually a little bit more open than the L shape, so it's a little bit larger. So we have 120-degree angle there in the middle, and then our smaller ones are going to be 30 degrees, which will equal 180. Right now, that doesn't really matter, but later on in the problem, just remember that. That's why I kind of have it written up there at the top, just as a visual reminder, so we can go back and look at it when it's needed. So we're going to go ahead and pull that pentagon out of there. It has 5 sides. So what we need to do is find the degree of those interior angles. So to do that, we're going to take 5x equals 360, because it's going to have to equal 360 total. So we're going to do the math there. We're going to divide both sides by 5, and we're going to get x equals 72. So we know those interior angles within that triangle that we're looking for, the NOQ or QNO, however you want to say that here, we're looking for that, and that is within that area of the pentagon. So the angles that I have labeled here in this pentagon that I pulled out, this one on the far left and this one on the far right, those are within that area that we're trying to find out. So it's important to know that those are 72. So if you add 72 and 72, you're going to get 144. We know that that inside point, the middle point here, is going to equal 144 degrees. This is where that previous triangle comes into play that I was telling you about. It's up here on the far right side of the slide here. That 120 is that same middle point. That is why it is very important to know that. So we have the 120 as the middle point, and we also have the 144. So to find out what portion of that larger angle is, we're just going to subtract 120 from the 144, and we know that NOQ is equal to 24. And next, we're going to look at number 6. It looks a little intimidating at first, but it's really not, I promise. So we see the girl standing away from the cliff. We see that she's holding a ruler in front of her face. What we're asked to do here is how the triangles are similar. Okay, so we see one triangle here, the larger one, from her to the cliff, which is going to be labeled DFE. And then we see a smaller triangle here highlighted in yellow. That's going to be from her eyes to that ruler that she's holding. So that one is labeled ABC. So what we're going to do here is we're going to look at the fact that, here we go, sorry about that. Okay, so we're looking at the angles E and B. those. If you were to blow up that smaller triangle that we have in front of her, the yellow one, if we were to blow that up to the same size as the other one, point E and point B are the exact same. So they are congruent to one another. And then we have angle F and angle C are congruent to one another. And then we have A and D that are congruent. So simply, what does that mean? We have angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. And another way to look at this is we have DE over AB. So that just basically means the line D and E, so from E to D, that line is the exact same on the smaller triangle as point A and B. Then we look at the line EF, which is the very end, the base of that triangle. It is going to be the same as point BC on the smaller triangle. And lastly, we have line DF, which is going to be the same as the line AC on the smaller triangle. Next, we're going to try to find out the height of the cliff. So here's our triangles again. And we know that 1 mile is equal to 5,280 feet. So she is a 1/4 mile away from the cliff. So we're going to divide the 5,280 feet by 4. So that's going to give us 1,320. Next, what we're going to look at is the inches. We're going to convert to inches. So we have the 2, which is the space, the length of her arm, the space between her eyes and that ruler. And then we're going to put that over 1,320. And we're going to set that equal to the 1.25 over the height of the cliff. But how do we know what the height of the cliff is? That's what we're trying to find. So we're just going to multiply both sides of that equation by 2. So here on the left, you see that that cancels that out. And then we're going to do the right side. So we're going to have 0.125 multiplied by 1,320. And we're going to divide that by 2, which gives us our final answer of 82.5 feet. This, the height of the cliff that she is looking at is 82.5 feet. Alrighty, thank you so much for going over Module 4 with me. I hope that helped you. If you have any questions, just let me know. Thank you.